Hi, I'm Ellie Pinches, an Education Officer here at the Royal Meteorological Society. In this series of short films, we are going to be covering some of the background information that teachers may find useful if they're teaching weather and climate at secondary level, and specifically if they're using our weather and climate teaching guide with accompanying classroom resources which can be found on our website Metlink, with links in the comments below this video. In this film, I'll be looking at the global atmospheric circulation, the patterns of circulation of the atmosphere and oceans driven by the sun. Have you ever thought about what makes the whole atmosphere move and rotate? Have you ever thought about what gives us defined areas of generally dry or sunny, warm and cold, or areas of high or low pressure? The answer to all these questions ultimately leads us to the fact that we live on a spherical rotating planet, at some distance from the sun. Some parts of the Earth's surface will always be pointing directly at the sun, whereas other parts are slanting away. Which parts of the Earth are pointing directly towards the sun depends on the time of year and the time of day. The image here shows the Earth at an equinox, when the sun is overhead at the equator. Where the sun is directly overhead on the equator, the sun's light is focused into a fairly small area, Area A. Whereas when the sun is low in the sky towards the poles, the sun's light is spread over a much larger area, Area B. Because it's the sun's light which warms the surface of the Earth, which in turn warms the air above the surface, it will always be warmest where the sun is highest in the sky. So that's the equator. The Earth's axis of rotation is tilted, and as the Earth orbits the sun through the year, the place where the sun is highest in the sky moves from the Tropic of Cancer in June, past the equator in September, to the Tropic of Capricorn in December, and then back to the equator in March. So you'd expect the warmest surface temperatures to follow the same pattern, maybe with a bit of lag to give the water and land surface time to heat up. Here is a typical temperature map for December. You can clearly see the warmest temperatures, those in red, are in the tropics, and the temperature decreases with latitude or as you go towards the poles. As soon as you have the situation when the air in some places is warmer than the air in the other places, you'll see the warmer air rising, and this is otherwise referred to as convection. With this in mind, we'd expect to see rising where the surface temperatures are warmest, so towards the equator, and sinking where the temperatures are the coolest, so around the poles. However, things are complicated by the fact that the planet is rotating. This gives rise to the Coriolis effect, the net effect of which is that anything moving in the northern hemisphere is pulled to the right of the direction it's moving, and anything in the southern hemisphere is pulled to the left of the direction it's moving. We'll cover this in more detail in Chapter 8, when we'll look at pressure and wind. So, consider some air that is rising in the tropics through the troposphere. The troposphere is the bottom 10 kilometres of atmosphere, where all our weather is considered to happen. When the air hits the top of the troposphere, it spreads out towards the poles, as it's very hard to get air to move past the tropopauls and into the stratosphere above. This is because the stratosphere, which is the layer above the troposphere, sees the temperature increase with height, making it very stable or resistant to vertical motion, just like fog trapped in a valley. In the northern hemisphere, the risen air will then start off moving from south to north, a southerly wind, as you will remember that we talked about wind from the direction which it's blowing from and not where it's blowing to. But the Coriolis force means that it is pulled to the right, becoming ever more westerly, until eventually the circulation breaks down, with the air sinking back down to the Earth and returning back to the tropics to take its place of the air which is rising there. However, that returning air, travelling from the north to the south, is also being pulled to the right by the Coriolis force, and now becomes an easterly, forming the easterly trade winds. The trade winds from the northern and southern hemisphere converge at the InterTropical Convergence zone, or the ITCZ. You would expect the ITCZ to track from the warmest latitudes on the Earth's surface from the northern hemisphere in northern hemisphere summer to the southern hemisphere in southern hemisphere summer, with a lag to account for the fact that land and water take a while to heat up and cool down. This graph shows the latitude of the ITCZ through the year. You can see that the ITCZ does move from the north to the south through the year. However, most of the time it is actually in the northern hemisphere. This is because the northern hemisphere is on average warmer than the southern hemisphere, partly because there is less land in the southern hemisphere and partly because the huge amounts of surface covered by ice at the Antarctic, much more than in the northern hemisphere. The ice reflects the sun's light before it warms the surface, and therefore the southern hemisphere is heated less. This circulation, rising around the equator and sinking around the subtropics, is known as the Hadley cell. A similar thing happens at the poles. The coldest air is found at the poles and will sink, spreading out towards the equator. Air spreading south from the North Pole is again diverted to the right by the Coriolis force, becoming ever more easterly, until again the circulation breaks down. The air warms as it travels equatorward, therefore rises and returns to the North Pole. This circulation is called the polar cell. Both the polar and Hadley cells can be seen clearly on the picture on the screen taken from Earth.null, which shows you near real-time winds on the surface of the Earth. On this day in March 2019, the InterTropical convergence zone is clearly just south of the equator, with easterly trade winds blowing in from either side. You can also make out the easterlies around the South Pole. What happens in between the two cells is a lot less obvious. Textbooks show the Ferrel cell with sinking air in the subtropics and rising air in the subpolar regions, and surface westerlies, which can be visualised as a sort of gear between the Hadley and the polar cells. However, the Ferrel cell is probably best thought of as the average of all the air motion caused by mid-latitude depressions or low pressure systems in this region. On this image taken from Earth.null, these depressions show up as swirling storms, clockwise in the southern hemisphere and anti-clockwise in the northern hemisphere, all carried on surface westerlies. So why are there westerlies and a jet stream in the mid-latitudes? Let's start off by considering two columns of air, one nearer the poles and one nearer the tropics. There is the same mass of air in the two columns, meaning the surface pressure at the bottom of each column is the same. However, the polar column is colder than the tropical column. As air, like any gas, expands when it's warmer, the tropical column will therefore extend further upwards from the surface of the Earth. So if you consider one of the dotted lines high up in the atmosphere, there is less air above the line in the polar column than in the tropical column. The air pressure on the line will be higher in the warmer air. Air moves from high pressure to low pressure, and therefore there will be air moving from the tropical column towards the polar column at that altitude. The air will get pulled to the right by the Coriolis force, and this will become westerlies. As the difference in pressure is zero at the surface but gets progressively bigger as the higher you go up, the winds also get faster the higher you go up. So there are westerlies at all levels, and the fastest westerlies are near the top of the troposphere, and this is called the jet stream. It is the fact that our mid-latitude depressions tend to come from the west that makes saying "red sky at night, shepherd's delight" one of the more accurate bits of weather lore. We will go on to this a little bit more in chapter 17 when we're taking a deeper dive into depressions. So how does this three-cell model of the Earth's atmospheric circulation give rise to pressure patterns? Consider a column of rising air, maybe at the ITCZ. There is divergence, or spreading out, at the top of the tropospores, and convergence of air coming together at the surface. The friction at the surface is far greater than the friction at the tropopause, where the air is thin and there are no trees, mountains to slow the movement of the air. This means that the divergence at the top is faster than the convergence at the surface, and therefore we are left with less air in our column, and the air pressure falls. So rising air is associated with low pressure. Air pressure is simply a measure of how much air there is above a given point. Similarly, sinking air is associated with high pressure. So we expect high pressure at the poleward edge of the Hadley cell, and at the poles. We expect low pressure at the ITCZ and where the Ferrel and polar cells meet. When there is air rising through the atmosphere, the pressure of the air falls as it rises up, and there is less atmosphere above it. As the pressure falls, the temperature of the air falls too, until eventually it reaches a point at which the rate of condensation exceeds the rate of evaporation, and cloud droplets form. When these get big enough, they then fall as precipitation. This is why we associate low pressure, be it in association with the ITCZ or in association with low pressure weather systems such as tropical cyclones or mid-latitude depressions, with cloud and rainfall. Therefore, where there is predominantly rising air at the ITCZ and in the subpolar regions, there will be lower pressure, cloud and heavier precipitation. Where there is generally sinking air at the poles and in the subtropics at the edges of the Hadley cell, the skies will be mostly clear, the climate will be drier and the pressure higher. These high pressure regions are the sources of our air masses, tropical continental, tropical maritime, and polar continental, which we'll look at in Chapter 7. The whole pattern of cells and surface winds shifts to the north and south with the seasons, further north in June and further south in December. Research has been undertaken to look into how atmospheric global circulation may change due to the changing climate. The 2013 Intergovernmental Panel on Climate Change report concluded that as the climate changes through the 21st century, we can expect to see the Hadley cell broaden, the track that mid-latitude depressions take shift towards the pole, and rainfall zones such as the ITCZ become narrower. The oceans also play a part in the global circulation. Together with the global atmospheric circulation and storms, both tropical cyclones and mid-latitude depressions, the global oceanic circulation is responsible for transferring surplus heat from the tropics to the polar regions and regulating the Earth's climate patterns. The large-scale circulations of the oceans is similarly driven by warm water rising and cold water sinking. In addition to this, where ice forms in the polar regions, it forms from fresh water, leaving its salt behind. This salt makes the water even saltier and heavier. The sinking of the water in the polar areas is therefore driven both by temperature and salinity, and is known as the thermohaline circulation. The full oceanic circulation is also complicated by the Coriolis effect, and also the presence of continents. The wind blowing also carries surface water. The Gulf Stream, which carries warm water across the North Atlantic to the UK, is a good example of this. Its polar extension, the North Atlantic Drift, is more closely linked with the thermohaline circulation. Together, they keep the UK approximately 5 degrees Celsius warmer than it would be otherwise. In 1992, a container full of rubber ducks escaped from a ship in the North Pacific. The ducks have been washing up on shores around the world since, providing an unintentional oceanic circulation experiment. Some ducks, however, have remained trapped in the Great Pacific Garbage Patch. Similarly to the atmospheric global circulation, research has been done to forecast changes to the oceanic circulation due to changing climate. The Intergovernmental Panel on Climate Change's 2019 Special Report on the Oceans and Cryosphere concluded that the effect of less sea ice forming in the Arctic is expected to weaken the Atlantic meridional overturning circulation, which is part of the thermohaline circulation. As a result, there will be an impact on the North Atlantic Drift. It is very likely that it will weaken and/or move. Although this would imply that the UK and other Western European countries would lose a source of warmth, the cooling is expected to be less than the warming caused by other aspects of climate change. In the next video, we'll be looking at the major global climate zones.